Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to demonstrate, how to apply momentum concepts to analyze an impact. So what we're looking at here, we've got this car that I've got labeled as car A, traveling at 50 miles an hour to the right, or we'll say that's east in this problem. We've got car B here traveling south at an unknown velocity that we're going to try to calculate. Now in this example, imagine they collide and they move off into the right such that their velocity makes a 60-degree angle with the direction east. In this example, it's going to be important to note that they're kind of stuck together here. That's going to be an important part of this problem. And again, when cars collide, they aren't always stuck together. I'm just throwing that in as an assumption in this particular problem. Now, important thing to realize is how to, or what concept to apply here. And momentum is the best place to start when you're analyzing an impact. If you're unsure of why, go back and review my video on why momentum concepts are used for impacts. Now, whether momentum is conserved or not depends on how you define your system. If this is my system, momentum certainly is not conserved because there's an external impulse acting on the system during the collision. And then if this is my system, also momentum not conserved. The key is realizing that if this is my system, the interaction between these two, the force interaction, is an internal force, and momentum is therefore conserved. So my momentum in this first picture should equal the momentum in my second picture, ignoring any friction or other forces acting during the impact. All right, so momentum is a vector quantity, so we should probably start by drawing some momentum vectors. So car B has a momentum, and that points down. Now, if I were, doing this, and I guess I am, I would label this MVB1 because momentum is mass times velocity. So this car's momentum is going to be its mass times its velocity. It's car B, and it's in picture 1. So MVB1 is the momentum of that car. Now, in this example, we're going to assume these have similar masses. That's why I didn't bother putting a subscript on here. If these were different masses, this would be a mass B times VB1. But in this example, just to keep it a little shorter, I'm going to assume these are virtually identical cars. All right, so the momentum vector for car A points to the right. And that's going to be MVA1. It's kind of hard to see that, but let me draw that a little longer maybe. Okay. So that momentum vector is the one I'm calling MVA1. So again, these vectors are momentums. They have units of kilogram meter per second. Right. This is the momentum of the system after impact. I've already drawn the vector. Its magnitude is going to be the mass times the velocity v2. And I'm going to go ahead and just put 2m because I've got two cars of mass m. That would add to 2m if they're identical masses. So if they weren't identical masses here, I'd maybe put something like mass A plus mass B. So the idea here is that this vector is equal to the sum of these two. What I'm going to do now is write a pair of equations here, equating the momentum for each direction. So conservation of momentum, x direction, calling right positive. When I look at my picture, this is the momentum before impact, MVA1. This does not have an x component to it, so this represents the total momentum before impact. That has to equal the total momentum after impact. Now, our momentum vector here is equal to 2mv2. That's the magnitude of that vector, but I want just the x component of it, and that x component would be adjacent to the 60 degrees. So I'm going to go ahead and multiply that by cosine 60 degrees. So the next equation I can write, conservation of momentum in the y direction. Right, as I look at my picture here, this momentum is in the y direction. I'm going to go ahead and just do down positive for this. So that's going to be MVB1. Whoops. I guess I just called it MVB1. So that's the net momentum of my system y direction before impact. That will equal the net momentum of my system after impact. Now, this momentum vector has a magnitude of 2m v2. And I'm going to multiply that by sine 60 so that what I have now is the y component. So this is the pair of momentum equations I can write for this problem here. Equation 1, equation 2. As I inspect equation 1, first thing I'll notice is if they're equal masses, these will divide out. And I should be able to solve that for V2 by taking VA1 and dividing it by 2 and then dividing by cosine 60. Interestingly enough, cosine 60 is 1/2, so V2 and VA1 are equal. In this case, 22 meters per second. Now that's just sheer coincidence by the numbers that I happen to choose. Usually this will not occur. Now that I've got V2, I can take that value, sub it into the second equation, and calculate VB1, keeping note that these divide out. So VB1 is going to equal 2 times V2 at 22 meters per second, times the sine of 60 degrees. And what I get out of that is, hold on just a moment, it's in the wrong mode there. Oops, I'm going to have to pause this for a moment here. My calculator's, I got to get the mode changed. Okay, I'm back, got that sorted out. So for VB1, I got about 38 meters per second. So VB1 going, considerably faster than VA1 here. So I'm going to go ahead and convert that back to mile per hour. So we got 38 meters over seconds times, if I want to convert that to mile per hour. My first conversion factor here, I'm going to put meters on the bottom, miles up top. There's 1,609 meters in 1 mile. And then if I want to get this from seconds to hours, my next conversion factor has to have seconds up top, hours on the bottom. There's 3,600 of these and 1 of these. So I'm going to go ahead and convert this now. 38 times 3,600 divided by 1,609. And what I get out of that is about 85. Now unit-wise, the seconds cancel, the meters cancel, and we're left with mile per hour. So in this example, which I completely made up off the top of my head, car B must have been going significantly faster than car A. Now, again, I want to go back and point something out here. This fact that the V2, this magnitude, ended up being the same as this is very, very unlikely. I mean, in most problems you work out of a textbook or something, that won't happen. That just came about because of the numerical example that I made up where they had the same masses and the 60-degree angle. That was just coincidence, but I do believe it's worked correctly. Important points of the problem are this. One, why to use momentum? Well, momentum is typically conserved during impacts, at least if the only forces are the impact forces between them. That's an internal force if we define our system like this. That's what allows us to equate the momentum before to the momentum after, typically. Second, how do we do that? We draw momentum vectors before and after. Each momentum vector should be labeled as a mass times a velocity. Then, if it's a one-dimensional problem, we just write a momentum equation in whatever direction they're pointing. If it's a two-dimensional problem, we typically write a pair of momentum equations, one for each direction. So I hope this video helps demonstrate these concepts. Have a great day.